Hello everybody and welcome to the ODTN demo from ONF Connect 2019, where we brought SDN and disaggregation in optical transport network for a multi-vendor solution for optical data center interconnect. The demo is done in collaboration between a few organizations, ONF, the Telecom Infra Project, a few operators, among which Telefonica, NTT, and Telecom Italia, and a group of vendors and supply chain partners, Adva, Edgecore, Lumentum, ZTE, NOKIA, Infinera, IP Infusion, Fujitsu, Sterlite, and the Metro Hall project. We wanted to bring SDN and disaggregation in optical transport networks in order to save CapEx and OpEx in data center interconnected deployments, achieve a rapid production adoption of innovation in terminal equipment, enabling vendors to innovate speed, reach, quality of transmission, but also enabling the operators to reap benefits by simple bookending, introducing then a better life cycle cost approach and optimizing the equipment lifespan, because there is a substantial difference between transponder lifespan, 2-3 years, and line system amplifiers or ROADMs, which can have a 10-year lifespan. Through SDN disaggregation, we also future-proof a service provider network, avoiding vendor lock-in. The ODTN solution starts with ONOS in the middle that uses open APIs for any control of the network, meaning that it uses OpenConfig to the two transponders, which are in the two data centers, and then it uses the transport API from ONF for the line system controller, or OpenROADM for the ROADMs. On top of ONOS, there is a deployment of a set of applications and drivers specific to the optical space. And those applications also expose transport API topology overview of all these devices that are controlled by ONOS to an operator OSS, BSS that can then request connectivity services among this whole network through ONOS. The whole ONF Connect demo is based on vendor-independent optical configuration and management workflow based on open APIs and so open source software. So this demo focuses on the transport API, OpenConfig for the transponders, and OpenROADM for the ROADMs. And through these APIs, we can discover optical equipment, open line system, ROADMs, and transponders, understanding what are their ports, the logical channel, optical channel, port statistics of the transponders, and have a consolidated and detailed topology view across a multi-vendor, multi-type environment. Then we can also set up an end-to-end optical connectivity with service wavelength tuning, with an automated wavelength calculation, and an automated setup that can span different topologies, both the one based on open line system and the one based on ROADMs and multiple vendors. Then we can also change the modulation of the transponders through the OpenConfig API in order to easily adopt deployment characteristics such as distance. And then we can also observe and tune the power information, both current input and output power, but change the target output power to adapt to loss, distance, and status of the deployment scenario. So over at ONF Connect, we had two Edgecore Cassini transponders with Lumentum ACO cards and two Infinera Group G30s, all managed by OpenConfig from ONOS. And then in the middle, there were two Lumentum ROADM 20s to constitute the line. Over at the Telefonica setup in Madrid, we had two NOKIA transponders, two ZTE transponders, two Fujitsu transponders, and an Adva open line system. This is the rack that has been used for the ONF Connect demo. On the top and the bottom, there are the four transponders, while in the middle, there are the two ROADMs. The two white transponders are the Infinera Group G30s, while the two black ones are the Edgecore Cassini with IP Infusion software and the Lumentum line-side ACO card. In the middle between the two, there are the Lumentum ROADM 20s that connect the two top ones to the two bottom ones. You can see this is the topology we have discussed. There is one host connected to the line side of one Cassini, which is connected to the Lumentum ROADM, to the other Lumentum ROADM, to second Cassini, to a second host. This Cassini you can see is manufactured from Edgecore. Software version comes from IP Infusion. There is also two Group G30s from Infinera. And you can see that at the moment these devices have configured 4 packet ports and 2 OCH ports. Same can be seen on the Cassini, which has one client port at the moment, and other line side ports. On the ROADM, you can see the many different OMS ports and fiber ports with a link connected to them. That is the link to the other Cassini. These two are the links for the line side port of the ROADM. That is line side to line side of the ROADM. That is the line side to ROADM. Also, the grooves are connected to the add drop of the ROADMs. At the moment, you can see that there are no configuration for any of the devices within the network, nor the Cassini, nor the ROADMs have any configuration in them, same as the grooves. There is nothing provisioned from an end-to-end perspective in the topology. From the optical UI, picking any of the transponders, you can see that at the moment there is no input from the ROADM on this Cassini device. There is no wavelength configured, and the modulation is 16 QAM. The Cassini is giving out some power, 4.60 at the moment, and but not receiving any from the ROADM itself. So what we can do is that we can try and change the output power, bringing it a little down. So we're going to bring the target output power to -6 here, so the tunable card will check and bring that power as closer as it can to the -6 that we asked for. As you can see, the same thing can be done on the Infinera grooves thanks to OpenConfig and the standard APIs. At the moment, the output power is -99 because there is no wavelength configured. So now what we're going to do is that we are going to provision an end-to-end connectivity between the two Cassini devices and the Lumentum ROADMs. That is done by asking ONOS for a bidirectional intent. So what it did, it was provisioning from the line side of the Cassini across this ROADM to the other ROADM to the second Cassini, and now we can see that each device along this path, in the case Cassini 2, has two configuration for the bidirectional intent on the -35 grid. The same -35 grid is actually the same one that was picked on the ROADM to achieve the line side the cross connection internal to the ROADM itself, both in the outputting and inputting sense, both from the Cassini to the other ROADM and from the other ROADM to the same Cassini. The same result can be achieved by asking the same configuration intent to the other from the two grooves. So what now is done is that it configured the -34 wavelength on the ROADMs to account for the end-to-end connectivity within the grooves. So if we take a look at the grooves, there's the -34 on those for the bidirectional intent. And now if we take a look at the optical UI, we can see that the Infinera grooves have now a -6.90 receiving power, meaning that the ROADM is receiving power, but the line side of the groove is not yet tuned on this one, while if we take a look at the other one, it's already tuned at -5 output power and has a wavelength of 191.4 terahertz, again with 16 QAM modulation. Also on the groove, as we have shown before on the Cassini, it can be changed the power, so we decide to bring a little lower, a little hotter, which is -3. And the groove actually has that -3 output power in the state. Also on the other one now, the power has gone closer to what we've set, which is 0, meaning that now the light is actually being capable of being carried across those two devices. And you can see that the ping between the two hosts connected to the two Cassini devices is actually now flowing. And that ONOS installed a certain set of rules through the intent subsystem. We actually have now two intents, two optical connectivity intents, one from the two Cassini and one from the two grooves to signal this end-to-end connectivity request. So what we're going to do now is that we're going to go inside the ROADM, which has these 4 wavelengths, and we're going to make the device, the ROADM, from an out-of-band connectivity, forget these rules, meaning that there will be a mismatch from what ONOS requires for an end-to-end connectivity to be there, and from what the device has in terms of capability in terms of configuration for the end-to-end connectivity. So we can see is that ONOS has those configuration, but we made the device forget about it. The ping stopped. Now ONOS will try and reinstall those rules because ONOS assumes to be the master of configuration, and if the device doesn't have a configuration that ONOS wants it to have or it was requested to it, it will reinstall it, and you can see that the device, that the ping is now started again because the device reaccepted that configuration that was given from ONOS to it.
As we previously discussed, this is the topology that is in the Telefonica headquarters in Madrid, where many transponders are connected on either two sides. Again, bookended transponders across an Adva open line system. The Adva open line system is connected through the RESTconf protocol and through the TAPI API. You can see that it has many OCH ports and that each port has connected to different links, same as discovered through TAPI. With the Fujitsu, again through OpenConfig, we discover many type of ports, and the optical one is connected to the line side of the Adva open line system. Again, same thing with the ZTE transponders through OpenConfig, we discover the ports, and in particular, this one is connected to the Adva open line system yet again. If we take a look at the ONOS CLI, we can see the same set of devices. In terms of ports, we can see, for example, in the case of the Adva open line system, the different ports that are exposed as a big switch. In case instead of the ZTE device, we can see the different set of ports again here, or same information for the Fujitsu transponders. And here you can also see the links that are in the system right now, connecting the multiple transponders to the Adva line system. So with this topology and the Adva open line system and different NOKIA, Fujitsu, and ZTE transponders, we can achieve the same end-to-end connectivity that was shown before with the Cassini and the Groove. In the interest of time, I'm not going to do that, but with the same exact command, the optical intent that was previously discussed, we can achieve the same end-to-end connectivity. And this comes to show the point that was made previously, that ODTN is capable of configuring a vendor-agnostic network with both ROADM or a complete open line system connected to ONOS and exposed as a big switch, as you can see in this topology, and many transponders, again through OpenConfig.
This is a very important milestone for the ODTN project because in September, October 2019, this solution that I've just showed you has been undergoing trials within Telefónica of Peru, thanks to the help of a great community with TIP and IP Fusion, Entity Electronics, Edgecore, Lumentum, and Fujitsu, which are bringing different elements to this setup. So on the ODTN roadmap, we want to achieve tuning of other and observation of other optical parameters, such as the FAC and OSNR. We want to achieve an integration with an optical planning tool, such as GNPy from the Telecom Info project, and also achieve an end-to-end power modulation workflow by negotiating these parameters end-to-end from the transponders or the power for the line system. And also we want to have a platform, platform hardening. So some takeaways: ODTN and the OPT group from TIP build an open source software stack for optical networks. Its open and device standard APIs in a multi-vendor environment enable the best of breed selection, best life cost cycle approach with rapid deployment, prototyping and testing of new devices and technologies. And within TIP and ONF, we create a common open source optical ecosystem with a strong industry consensus to achieve optical disaggregation. If you have any questions, please visit the wiki at wiki.onosproject.org or send an email to me, Andrea@networking.org. Thank you.